Today we'll look at what is Hadoop. If you've heard of big data, I think you've definitely heard of Hadoop. And in my world, as a data engineer, this is one of the turning points where we started using massive amounts of data, and started using parallel computing in a huge level. And um, let's get into the slides and understand what it is. Um, so Hadoop is a framework that allows distributed computing. What distributed computing means is you can have your data set split across multiple processing nodes or servers or computers, and all those nodes together are called a cluster. Those cluster of computers hold the large data sets. So the large data sets cannot fit in one particular computer or server or node. So we put them across a cluster of multiple nodes, and we also have computing power in each of those nodes. So it has like CPU, RAM, and it also has a hard disk or a SSD that contains a lot of data. So that is one computer. That's a node, and that computer is called a node. And there are multiple nodes like that split your data into and store it on each of those nodes. And why is this also advantageous? Like in case of availability and failure, that's another important point. uh, how can you scale up? That's another important point. So we look at those two things now. How is it able to scale up? So tomorrow, if you need to add, um, say you are running a website and you're getting 1 million customers today, and suddenly there's a promotion and there are 1 million more customers that show up in the next week. So how do you scale up? You can add more nodes to it, and then Hadoop will redistribute the data into the new nodes that you add up. That's how you actually scale up. So you can just add one server because you just need a little bit more, or you can just add 1,000 more, and then you can connect them to the cluster, and all those become nodes of the cluster, and then Hadoop can scale up and then store the data across all those machines. And not only that, another important thing is we don't rely upon the high quality machines, servers that you buy from IBM or HP or Oracle to store these datas. These are called um, hardware or computers that are easily available, and you use them to build this Hadoop ecosystem. So you don't have to buy a very expensive hardware for this. You don't have to buy a specific appliance for this. So if you worked in like Teradata or Netezza, you know that you have to buy their own appliance, which allows you to store a lot of data and scale up. So in this case, in Hadoop, you don't have to buy a specific um, um, tool for that. You can use commodity hardware. So you can buy any Linux system and add that to the cluster. Um, so you don't have to really buy a high quality appliance sold by like Teradata, Netezza, IBM, or HP or Oracle or stuff like that. Um, so at the end of this line, we are also talking about something called highly available. That's something that's really important for Apache Hadoop. Why is Apache Hadoop highly available? Is because each node stores multiple, like each data is split into each data point is stored in multiple copies across multiple nodes. It's called a replication factor. So you typically store 3 copies at least of all your data. So like, and the advantage of that is you get a highly available system. If you have say data for customer A in node 1, 99 and 1099, if 1099 fails, you still have the data in 2 other nodes. So you're still able to get the data. You don't have a time where, oh, this customer's data is not unavailable, right? So you don't have to ever talk about that. So that's what the highly available service means. And Apache Hadoop, since it was introduced, has the ecosystem has evolved and added a lot of products around it. The base Hadoop just involves these four libraries, which is a Hadoop common, which is not anywhere mentioned in this slide, in this picture. The Hadoop distributed file system is the base of how the files are itself stored. Just like Linux has its own file system, Windows has its own file system. Hadoop is not using those file systems because it's distributing the file systems and storing it in a different way. It uses its own file system called HDFS. So that's it's a distributed file system. It has high throughput, and it splits the data and stores it in multiple nodes. That's all you have to know right now. Hadoop Yarn is a job scheduling framework that sits on top of HDFS, and what it does is it allows like a Spark job to go and access all the HDFS files. It allows the Kafka process, stream processing, the Spark MLlib, the Pig, the Hive, the Scoop, anything that you run on top of Yarn uh, goes through Yarn, and Yarn is the resource manager. Yarn is the resource manager that uh, schedules jobs and manages the jobs between multiple nodes. And at the base of all this is something called MapReduce. So in between Yarn and HDFS um, is something called MapReduce. So the when Yarn like accesses submits a job, uh, like when you write a Hive SQL, so like after you get to understand what Hive is, Hive you can write SQL to actually retrieve data from HDFS. Say you're writing a Hive SQL and you're selecting some 1,000 records from one of the tables that is set up as a Hive table, and its base data is actually in HDFS. What Hive would do is it'll actually convert the Hive SQL code into a MapReduce job, which is a Java based framework, and it uses Yarn to actually submit those jobs. So Hive converts SQL into a MapReduce code, and Hive calls the Yarn to actually submit those jobs, and Yarn takes care of submitting the jobs across multiple nodes and getting the information back and storing that. So that is these four are the most basic, and those are like the core Hadoop elements. Everything around that has been built that you can see here, whether it's like if I come from the right here, the purple one is Pig, which is a scripting tool. There are machine learning tools like Mahout, Apache Spark MLlib, uh, again data piping tools like NiFi, Flume, and Scoop. Scoop is something we'll pretty much talk about today. Pretty important. That's where we write something from a SQL table to Hive to Hadoop, or from Hadoop to the SQL tables. So Apache Solr for search engines, it used to be very popular. I think I have not used it. NoSQL database like Apache HBase, um, SQL over Hadoop. This is pretty important for any kind of visualization, BI tools. Sometimes data scientists uses BI, business analysts use it. So for SQL or Hadoop, it's Hive, Impala. Apache Drill has not been as popular these days, but it used to be one of the most important tools earlier. For stream processing, like Storm and Kafka are very popular. For in-memory processing, Spark. I think Spark is one that I've been working on for the last 3 years, and it's been taken up very much by data engineers and data scientists. So that's pretty important. To the leftmost top here, we talk about Apache Ranger, which takes care of the whole ecosystem security. So giving access to people, giving access to certain data sets, all that can be taken care by Apache Ranger. To the rightmost, we look at the data formats such as Parquets, Avros, ORC, and Arrow. I haven't heard of Arrow, but the Parquet and Avro and ORC, those are pretty efficient compared to a typical text file or a CSV file or something like that. So those allow for like Parquet and ORC allow for columnar structures. Avro allows for row-based structures. They also allow schema to be noted. So because of that, uh, like your programs can understand what schema the file is in, and it can understand that the fifth field is a string, the seventh field is a integer, and the 10th field is actually a long. So because of that, it can process it much more efficiently. The programs can process it most efficiently. Also, because the um, metadata of that file is already known, if you know the format of the file, we could also compress it much better. So that it helps. Those data formats are very advantageous because of compression, faster processing, and your programming being simpler. So to the leftmost here, we see something called Zookeeper, which is coordinates and manages your whole node ecosystem. Say if a couple of nodes fail, then Zookeeper is the person who's going to notify that, try restarting that, and if possible, like get them back uh, to normal health, and then know the node, like make sure Hadoop knows that those nodes are back up, so that those can be used as well. So Zookeeper is where it coordinates the nodes to make sure they're all healthy. If not healthy, then take the action that it needs to take care. It's slightly confusing with Yarn. When I first learned about Yarn versus Zookeeper, I did get confused. But Yarn is something which goes to the nodes and submits the jobs and takes care of the jobs. And when the jobs complete at one node versus not in the other node, and it waits for the other nodes to complete and then coordinates that output input between those jobs. Zookeeper is actually where it actually coordinates the nodes. So if the node is down, the node is working, node is not working. So all those things are done by the Zookeeper. So let's first look into the most basic part of Hadoop. Other than the common utilities that Hadoop has, the most basic form of storage is HDFS. So as we already slightly looked into this, this is a distributed file system. That means the files are split and stored across multiple nodes. So that it also provides high throughput access. What does that mean? So you're able to read at a much faster speed because there's something called partitions and bucketing, which you learn. So you're able to like read it based on partitions and buckets. Also, there is the Hadoop stores it based on a larger block size than a typical Linux file system. In a Linux file system, you'll probably have a very small block size. In Hadoop, it's typically like 128 MB, 64 MB at least, or I've seen 256 MB, 512 MB. So depending on the system, the size of the system, the type of jobs you run, your block size could be much larger. And larger the block sizes, each block size will have one map processor. I mean, what that means is there'll be one processor running for each block, and if a block itself is like 512 MB, so you'll have, if it's a 10 GB file, so you'll just have 20 different processes running. So you'll have 20 different processes running, all of them can do it parallelly, so that makes it high throughput. So just to explain high throughput, so if you have a huge 10 GB file in one node, that can be like accessed by each blocks differently, and each of those blocks can be processed by a different process. That makes it high throughput. So your application can run really fast because of that. Hadoop MapReduce. This is something that is basic to Hadoop. It's a software framework for processing large sets of data. Let's look at the bottommost point here. I spoke about high throughput, but what is highly fault tolerant? So I think I spoke about this a little bit when I spoke about how Hadoop is fault tolerant. So the way HDFS is fault tolerant is because if one of the nodes go down, there's always a copy of it, at least in two other places. I mean, you could change the replication factor to be 1, but that's not recommended. You won't have a highly available system. So it's the default is 3. So if you have a 3 replication factor, what that means is each piece of data is copied thrice, and you have 3 copies of the data in multiple nodes. So if even if one there's a fault in one node, the other 2 nodes would still be processing, and your Zookeeper will um, um, let the node that is failing either restarted or taken away, or do something so that the replicated data on that node will get either, if this node cannot be restarted, Hadoop will take care of copying that 2 other copies there into the third copy in another new node that comes up, or in a node that has space. So it'll copy it over there, and it'll still have 3 replicas. So that's why it's fault tolerant. High throughput is where you read it in blocks, and you can read it through in parallel processing, so multiple threads can read it. It's suitable for application with large data sets. So typically it is built, it is, if you're not talking about terabytes, if you're talking less than 1 terabyte, Hadoop is not the system for you. If you're talking about less than 10 terabytes, you probably can still do with other processing hardware. But yeah, if you're more than 10 terabytes, Hadoop is like really ideal for you. And if you and as I earlier said, we can build it using commodity hardware. You don't need a specific system for this. You don't have to buy a specialized server for this with specific kind of features. All we need is a very high RAM, say a 64 GB RAM or a 16 GB RAM, something like that. A very good processor, say a 16 core processor, or a 8 core processor, and a very good hard disk or SSD, say a 1 terabyte SSD, or 500 GB at least, or 2 terabyte SSD. That would be ideal. So if you buy any hardware from which has these kind of specifications, and also the network speed, so we also need, because all these are connected by network, we also need a gigabit per second kind of network speed, so that we can make it work. So we spoke about HDFS. Let's get into a little bit of HDFS architecture. So there's something called name nodes and data nodes. So why am I getting into here when I'm talking about HDFS is because when we store the data, we store them in nodes, but specifically we store them in something called data nodes. So data nodes are the nodes. In some architecture, it's called a slave, and the name node is actually the master. But essentially, name node is a controller, and the data nodes do the work, are the worker nodes, and the name node conducts these operations, because it knows, name node has the metadata of all the data, where it resides, how many replicas are there, which replica is there in which data node. So all that information about which data piece is in which node, all that metadata is stored in the name node. So name node actually can control the multiple data nodes. So if you know, HDFS is fault tolerant. If any data node fails, you can like, because there are other 2 replicas, we can always have it. But the name node, there's only one name node. So if the name node fails, we typically set up something called a secondary name node, which can take over from the name node and then take it up. But it's not there is not 2 controllers at one point. Always there's one controller. The name node is the only controller that can actually issue commands to the data nodes, and coordinate between the data nodes. And in case there's a name node failure, we typically have a secondary name node which can take over to be the name node, and it can it'll it'll be designated as the name node. If the name node if the real name node fails, the secondary name node will be designated the name node, and then after it's designated the name node, then it can now coordinate all the tasks that name node used to do. So this is something we need to understand about the data nodes. The data nodes are the ones that manage the storage. They're all interconnected, but they need not be in one location. They need not be in one server rack. A server rack is where you have a set of servers um, piled together and connected by a single network and electrical system, cooling system. So that is one rack. You could have multiple racks in the same data center, or you could have it in multiple like different data centers, which are like states apart, cities apart, or even countries apart. So you can have, depending on how big your system is, like if you have like 50 servers, which is typical for a production instance, you could have it in multiple data centers, say 3 different data centers, and all 3 data centers need not be in one state. Say if you're a nationwide provider of information and you want this information to be there even if East Coast goes down because there's a electric outage in East Coast, so you can also have this in 3 different geographies. So you can have 3 different data centers in 3 different geographies, and those 3 geographies could talk with each other. Okay, so HDFS exposes a file system namespace. So the namespace is provided back to the user. So if you see here, it says home foo data, and then that is what is exposed to the user. So the user can actually, just like in Unix or Linux, you can go through the folder system, or in Windows you can go through the folder system. So HDFS actually provides a similar like data entry point. You could use that. So what the data nodes do, they serves read write requests. So any read request, somebody's looking for information, or write request, somebody's adding more information, everything is done by the data nodes. They create the blocks. So whenever we write a if the data block size is like 200 MB, sorry, if the data size is 128 MB, which is typical for most architectures, and if the new file that's coming is 200 megs, so 200 MB, so the first 128 MB will be in the first block, and the remaining whatever is remaining 72, the remaining 72 MB will be in the next block. So HDFS will allocate a 128 MB, 128 MB blocks. The first 128 MB block will be full, and the second 128 MB block will be filled only until the remaining portion, because out of the 200 MB, remaining 72 MB is there, so it will only fill the 72 MB, the second block. So that's how block creation happens. It takes care of deletion of blocks. It takes care of replication upon instruction. So when the name node asks the data node to replicate, then the data node replicates it. So all that is done by the data node. So let's take a little bit of an example. Say somebody puts in a file called transactions.avro. It's a 256 megs file, and this cluster has a block size of 64 MB. So because we have a block size of 64 MB, we split the 256 MB file into 4 blocks: block 1, block 2, block 3, and block 4. And each of them is 64 MB, because the block size in this Hadoop architecture is 64 MB. Now what happens is there's a replication factor of 3. So the name node now has to store these 4 blocks across these 6 nodes, and it has to make sure each block is copied in 3 places. So if you look at this, what happens is the name node has a blue block 1, and it notes the addresses of that. That is, the blue block 1 is stored in uh, data node 1, data node 4, and data node 6. And then if you see the actual data nodes, you can actually see that in the data node 1, you can see block 1. In data node 4, you can see that there's block 1. And then in data node 6, you can see that there's block 1. Similarly, all these addresses are stored in the name node. And then actual data, the blocks itself, are stored in the data nodes, the right. So the name node just has all the block names and where they are located, where the 3 replicas are located. And in the data nodes, the actual blocks get stored. So the block itself gets stored in each of these data nodes. Okay, so that I should have given you a little bit of more information about that. So we spoke about block sizes and blocks. It's a little bit of like help to understand this, especially when we get into complicated MapReduce programs, and like when we want to optimize how we do the MapReduce programs. So let's understand that a little bit more. HDFS stores the data in blocks. So even if you have a file which is like 10 GB, it breaks it into blocks and stores it in HDFS. Blocks are physical partitions of data in HDFS. Just like blocks are in Linux or in like Windows. So like if you know blocks from Windows or Linux, yeah, you exactly understand what this is. When a file is loaded into HDFS, it's split physically, and then it's split into multiple blocks, and we set that up in the HDFS site.xml. So in the HDFS site.xml, which is one of the config files, we set up a parameter called dfs.blocks.size. So depending on how much we set that as, again, typically it's 128 megs, but you can set up different things depending on your like need. So we set it up as 128 megs, and then that it splits into that size. And as I said earlier, Linux has a much smaller block size. Windows has a much smaller block size, but Hadoop has a much bigger block size, like 128 MB, because it wants to like it wants to be able to process huge amounts of data, like petabytes of data. I have never dealt with petabytes of data, but yeah, hundreds of terabytes of data I've dealt with. So typically, Hadoop makes it possible because you have a much bigger block size. So Hadoop is able to handle that better by doing it in megabytes. So here's an example where you have a file size which is 1 gig, which is 1024 megs or 1024 MBs. If you have a 128 MB, then you will get 8 blocks of 128 MB each. So so that if you have a 1024 megs file, that means you will get 8 blocks. So if you have a replication factor of 3, then you will have to store 24 files. So 8 times 3, 24. So we store 24 files. And name node will have to note all those 24 files metadata. So it will have to know which block it is, where is it stored. That's the metadata. So that data gets stored in the name node. Say if you instead of doing it as a 1024 MBs, say you have it as 4 KB, then you will have a 250,000 blocks. So you will have to create 250,000 blocks. So just think about how big your name node metadata will be. So even if you have to find a file, it has to go through the metadata list and find out all that information through the 75,000. I mean, now without replication, this is 250,000 blocks. When you replicate it 3 times, it becomes 750,000 blocks. So in the name node, we'll have 750,000 records. And if you're finding for, say, customer A, and name node has to find out where that block is, it goes through everything, and it just cannot find it. So it's impossible for your name node to be able to like look for that particular block of information. And note that this metadata information is stored in memory. So that's why we don't want to have a small block size. All this will be stored in memory instead of storing in the hard disk or SSD. now again, the block size is not like, at the same time, we don't want to set it as like 1 GB or something like that, because each block of data, there's one mapper that's launched. So for now, if you don't understand what mapper is, like it's kind of like one task that runs whenever you run a SQL query in Hive, or whenever you run a MapReduce job. Uh, the map job runs multiple tasks for each block of data. If there are 750,000 blocks of data, then your map job runs 750,000 tasks. Rather, if you have 8 blocks of data, then your mapper will actually run 8 times. So 8 different tasks will run. Each task will process that particular block. So that's the advantage. So that's why you have to like keep it somewhere in between, and typically most applications keep it as 128 megs. Next, we look at split size. In Hadoop processing, there's something called splits. These are not actual physical files being divided into blocks, but these are like logical chunks of data. So when Hadoop splits it into 128 megs, say the first record until 100th record crossed 128 MB. So in the 100th record half, you actually got a like you reached 128 MB. So Hadoop would just cut the file right there and then store it as a block. It doesn't really respect like record by record or like JSON by JSON. It doesn't do anything like that. So it doesn't care about it. It just split it by the number of megs. And say if you have a file of 400 megs with 104 lines, each line having 100 megs of data, you'll get 3 blocks. 3 blocks of 128 MB, and then 1 block of 16 MB, which totals to 400 MB. But like when your input split is actually processing your data, you need to keep that file boundary or a record boundary in mind. So we'll actually have to think about 4 splits. So a block is different from a split. Split takes into account the logical separation of files or records, but your block size doesn't. That's the difference. And split size can be set as a job property. Right? So when you run the job, you can set up the file input format split.max size. You can set that up in the so the split size can be set up when you do the actual job execution. Let's get into MapReduce. I know we spoke about MapReduce a little bit, but what is MapReduce, right? MapReduce is another core element of Hadoop. So it sits right above HDFS. So HDFS is where you store your data. MapReduce is where you process your data. So MapReduce is a processing technique and a program model for distributed computing. So when you write a like Java program on a non-distributed environment, you typically process each file separately. But what if your data itself is split into like multiple blocks and they are in multiple computers? How do you do that? So that's what MapReduce is solving. So the MapReduce program does 2 things. One is map and then reduce, just as the name suggests. What map does is it converts all your data. So it kind of flows. If you have like 100 records, it converts all your data into whatever needs to get done. So if there are 100 records in your input file and you run the map job, the mapper processes each of these 100 records one by one and processes that element. So if you want to say change the date format, you have an input date which is actually coming in as a string, but you want to change it into a like a real date format. You want to read the date and then see if there are first two elements are the second two elements are dd, and the last four elements are like YYYY. And then if it is matching that format, then you want to convert it into a like date. So all that means you need to process each record separately. So for any kind of processing that has to happen at each row level, then that part gets done by map. Um, like after that, we get a tuple out of it. So there is a key value pair, which is um, say for example something comma something. That's a key value pair. So if like those key value pairs are used to get into the reduce task, where we kind of combine data into smaller set. Say for example, after you convert all this, after these 100 records date get converted, you want to split it by year. So if there are 3 different years in your data set in your 100 records, you want to split your record by year, and for each year you want to calculate the total value of one of the numeric numbers. Say this is all sales records, and you have like 100 sales that are there in that file, and each file has a date and a sales amount. If your output needs to have like each year that happened, so there are 3 different years, so list the years and the total sales in each year. So that's the output that you want. So when you run the MapReduce job, the map takes care of converting the dates into different date formats, and you can also do converting the date from the date format, figuring out what year it is. So you can do those two things in the map portion of the job. And when the reduce happens, it can actually combine all the elements that have the date as the year as 2019 to be together, 2020 to be together, 2021 to be together. So it can do those 3 things. It can combine those records and then give the output that you need. So there's a map that needs to happen. There's um, a reduce that needs to happen. So if you want to do those 2 things, you separate those as 2 different tasks. And because these are happening in multiple computers, map runs in each of the nodes, and then when it actually has to combine, like somebody has to combine it together. So that part has to happen when the reduce happens. So the reduce has to do certain things called shuffles, and like it might have to sort, it might have to analyze what data is where. So it might have to do a lot of those things. So all those things, inputs and combines, whatever tuple we got, it uses those tuples to combine them and reduce them and provide us the output, which is like year by year sales. So always the map job happens first, then the reduce job happens. Let's look at into a stage by stage. So if you look at it, map is like one stage, and reduce itself is like 2 stages. So there are totally 3 stages. Map is one stage, which what it does is it processes all the input data. The input data is form of a file, like a directory of lot of files. All those things can be the input data, and the input file is passed to a mapper function. So the mapper function will actually tell what to do. So for our case, we need to convert string to a date and pull the year from the date. So that can be written into a mapper function. So you write a function, and you write the functionality that it needs to do. And if that is written as a mapper function, then what Hadoop will understand is, let's process all these records to the mapper function. So that's what it will do. After the mapper function runs, it creates several small chunks of data. So you get lots of data in each node. You'll have several small chunks of data. Now is where the reduce stage comes in. So the reduce has 2 different things. One is the shuffle, and next is the reduce. And reducer's job is to process the data that comes from the mapper. So whatever comes from the mapper, the reduce can actually take it up and start processing. After processing that, it produces a new set of output. and that output is going to get stored back in the HDFS. So every time you run one MapReduce job, the input is read from a HDFS. So the input is HDFS. After that, the processing is not stored in memory or something like that. It gets written back. So it gets persisted. It gets written to the hard disk, and it's stored in HDFS format. So if you look at the bottom table below, I'll tell you a little bit more about how the inputs and outputs of the maps and reduces are. So when you write a map function, your input is a key and a value. Like the output would be a list of key value pairs. So each key value you get back a list of key value pairs. In a reduce, what happens is you get a key and a list of values, and that gets like processed by reduce, and then we get a list of key value pairs again. So for our example, like when we have the input in the map function, we have like the dates and the sales, and the dates and the sales as input. We process the date and get the year out. So we get the year as the key, and then the sales as output, like a set of sales and year and date formatted sales date and string formatted sales date. All those can be part of one value. You don't have to have just one field as one value. You can have multiple fields separated by commas or separated by pipes as one value. So the key here will be the year, and the value will be a list of number of columns. And then when the reduce happens, the key and the list of values get read, and then it combines all the years that are same together, and then in the reduce function we will want to add the multiple values that are there. So in the reduce function we write a function to add with the other values. So we write that down because we want the sum of the sales. If you want the average of sales, we just write the reduce function differently. So that should explain a little bit about the map reduce. Let's move on to the next topic. Actually, MapReduce is pretty complex, so we can't move on to the next topic. So let's look at this input. So we have an input where we have XBB, CBA, XAC. So if you see 2 X's, 3 B's, 2 A's, and 2 C's. So essentially, when it gets split into multiple processing, so it gets into some random order. So you can see C, the first processor has X, B, and B. Next one has C, B, and A. The next one has X, A, and C. Say those are the 3 nodes that are processing the data. The map then maps X to 1, B to 1, B to 1. All that does is it's counting each of the operations here. So in this example, what is happening is it's counting the number of X's, number of B's, number of C's, number of A's, all that. So to do that, what the map would do is map function would actually see what is in the left and then output the value 1. That's it. It doesn't do anything with it. It doesn't check what the value of the key is. It just returns the value 1, because all we have to do is we want to count it. So if there are 10 of them, we keep adding all those ones, we'll get 10. So all we have to do is like if when the map we give it as 1, and then when we combine it, we just add all those numbers and group by that X, then we'll know how many X's are there. If we group by B and then add all those ones, we'll know how many B's are there. So all we have to do is that. So when the map happens, all it does is the function adds in 1 for everything. It does not check what value it is. It just checks 1. It adds 1 for everything. Then what happens is the combine operation happens. So everything to the right of map is actually part of the reduce operation. From combine to partition to reduce. So everything is part of the reduce operation. So in the combine, what happens is the X's go together, the B's go together, the A's go together, the C's go together. Now you see we have values like A1, A1. If you reduce that, that is we add all the A's and add all the values in A's. That is we get A and 1 plus 1, which is at the end we get A2. Here we have B, and then it's 1 plus 1 plus 1, that's a 3. In the C, and then 1 plus 1, which is 2, X, 1 plus 1, which is a 2. So those are the steps for MapReduce. I think let's move on from MapReduce now. Let's look at the other pieces of the puzzle. Yarn is another core element, and this is the last core element of Hadoop. HDFS, um, Yarn, and MapReduce, along with the Hadoop core elements. These are the Hadoop, like the basic Hadoop ecosystem. So when you install Hadoop, these are the things you typically get. And this is from Hadoop 2 onwards. Like before that, Yarn was not there. So um, Hadoop 2 onwards, these are the four pieces that when you just install Hadoop, you get all these components. Anything above that, like if you want Hive, if you want Scoop, you have to install above that. So it's not part of the core Hadoop solution. So what's Yarn, right? So we spoke about Yarn a little bit earlier. So whenever somebody submits a job, so somebody runs a Hive SQL, somebody runs a actual Java MapReduce job, or writes a pig script or anything, like even Spark query. So all those are handled by Yarn. Um, Spark may be a little different because it doesn't run a MapReduce job, but all other examples I gave you actually converts into a MapReduce job. But Yarn's work is not really whether it's MapReduce or not. Yarn's work is to get like Yarn has a resource manager, and then it manages the work across all the nodes. So the job submission happens across all the nodes, and they talk to each other through the resource manager. So the Yarn has the resource manager, and then that helps coordinate all this work. So there is so if you look at the components, the resource manager allocates the resources for the jobs and schedules the MapReduce jobs. So it allocates system resources for each of those applications. So if an application wants to submit a job, it gets some RAM allocated, some hard disk allocated, some memory allocated, and then it can actually use the processor as well, so it can get that job submitted. Nodes manager is where the allocation of resources such as CPU, memory, bandwidth, and the monitors the usage. So nodes manager does that. The application manager, it performs the interface between resource manager and the node manager, and it performs any negotiation that's needed. So if some more memory is needed, all that is handled by the application manager. It also further works with the node manager to monitor and execute the subtask. So the whole task is monitored by the resource manager, but the subtasks, because the app manager, the application manager is on each node, so that will take care of monitoring the actual app that got submitted. So if there are two clients submitting two different jobs, there'll be two different app managers, and those two app managers will take care of the local processing of those apps. A resource scheduler allocates the resources to various running applications, but it does not monitor the status of the application. So if there's any failure, like your resource scheduler will not really restart the job. So that's Yarn. I mean, I use Yarn all the time, but I'm not an expert in Yarn. So let me move on. Zookeeper. So this one is sometimes confused with Yarn. That's why I had it immediately after Yarn. But it is not. I mean, as long as you understand what the difference is, you'll be easily able to understand it. Zookeeper coordinates the various services in the Hadoop ecosystem. So if there's like multiple services that are running, it coordinates the various features in the distributed environment. It saves a lot of time by synchronizing it, maintaining configuration, grouping them, naming them. All those things are taken care by Zookeeper. Zookeeper improves speed, like when the workload is heavy, it takes care of like how fast the workload is. Its reads are more than write. Organization, so it organizes like all the transactions, that if Hive does something versus Spark does something versus like Spark SQL does something versus Scoop does something, it organizes all that by keeping a record of all the transactions. It maintains a single hierarchical namespace. So just like we have directories, it maintains the namespace of all the different elements. It can be replicated over a set of hosts. So you can have a Zookeeper over multiple hosts, and all the instances know what other instance is doing. So it's kind of reliable. And as long as the major servers are available, Zookeeper is kept available. Okay, that's Zookeeper. Let's go on to Hive. So we use this all the time. Hive is going to be pretty important when you work as a data engineer. So Hive is where we can submit SQL queries, um, SQL-like queries. So it's called HQL, but you can submit SQL-like queries like select column 1, column 2 from table. You could say like you could say limit so many records. You could say you could have a where condition. You could have all those typical things that you do as a SQL query language. You can do that in HQL. So let me give a pause here. Over the last 3 years, I've seen that most people don't use all parts of the Hive. Hive is really important. It's part of the Hadoop ecosystem. There are parts of Hive that we still use, but we don't. For the last 3 years, I've not seen most clients using Hive to run queries. Rather, they use a part of Hive like metadata store. They use the uh, yeah, I mean the metadata data store is one that is pretty important, because if you want to run an Impala query, if you want to run a Spark SQL, if you want to like do something else with it, I think the Hive metadata store is pretty important. Um, but I've seen that people install Hive and use it rather for a metadata store, and they use the other tools that happen with it. And the reason for that is Hive is pretty good at making it easy for a SQL person who knows SQL to actually run MapReduce jobs. So let me back up here. I should first talk about what Hive is. So Hive is a query language. So you can run a query language and you can process that huge distributed data set which is in Hadoop. You can process that information. You can run a select query and look at the data. You can just look at a few pieces of records using a where condition. You can do all that using a Hive query. You cannot do like updates or anything like that. So it's not every SQL command that's supported. But if you know SQL, it's easy thing to learn. Like if you don't know like core Java with MapReduce functions, and you're not, or you know it, but you don't want to write programs all the time because it's going to take much longer to test it and ensure that is like deployable in production. If you want to do something quick, the Hive SQL helps you a lot. That's the huge advantage. The disadvantage is that Hive takes a long time, and compared to the latest uh, like Apache tools like Impala, Drill, like Spark SQL, Hive is pretty slow. And what Hive does is, in the background, it converts your SQL into a Java MapReduce job, and it submits the job using Yarn framework, and it gets back the result just like a MapReduce job would. So you all this happens in the back end, and given Hadoop was like developed to be a batch environment, batch processing environment, even these Hadoop jobs get submitted. It typically takes like 40 minutes, sometimes 10 minutes for a query to come back. It's not really interactive query running. So it's that's the kind of framework Hive runs in. So let's go back to what Hive is. So Hive comes with two components. One is the JDBC drivers and Hive command line. So with Hive command line, you can go into a black screen, run this Hive commands, and then wait for the command to come back. Or you can connect it using a JDBC driver, run it in your like any tool that you have, any Toad, any kind of data tool that you have. You can connect it to any BI tool like Power BI. You can connect it to Tableau. You can connect it to any kind of BI tool, any kind of SQL client that you have, and you can run it using those JDBC and ODBC drivers. So that's how you typically run Hive queries. Um, it allows both real time and batch processing. So if you have a very small query like limit one, just get me one record, you can run it quickly. It comes out in a few seconds, and then you can use it for real time processing. But typically, Hive is used for batch processing. So if you want to run a job where you want to like summarize your sales by year and then run that and then write that back to another HDFS file, yeah, you can submit a batch query and then it runs and it gets back the output. Okay, so there are four components of Hive that you need to understand. The metadata store, as I said, this is where when you create a table, you write a create table statement in Hive, and then it stores that information, like what are the fields, what is the table name, what are the like column types, is there a like um, is there are there any constraints for the table? So all those things get stored in the metadata store. So that's pretty important. Even if people don't use Hive, this metadata store where you create the table, uh, that that table is important, because if you use a Spark SQL, you use the same name that you created in Hive to actually um, no, I'm not sure if Spark SQL does that, but say Impala or something, you need the table to be defined in Spark to be able to use it across in in Impala. So that's the metadata store. It stores all the metadata information for all the tables. Driver actually manages the life cycle of the HQL statement. So after you run it, the driver is the one that pulls it up, converts it into a MapReduce program, runs it, then provides the output out. The query compiler compiles the HQL into a DAG. A DAG is a directed acyclic graph. What it does is it pulls it into multiple steps, which run one after the other. So here, what the acyclic means is it doesn't circle back into a cyclic like multiple processing job. It typically runs one after the other. So it's like A, then B, then say C and D, and then after that E. So it's like an order of tasks that have to happen, or order of jobs that have to happen, that that comes out of the compiler. The query compiler comes out with that kind of DAG, and the Hive server provides interface. Like if you install a Hive server, you get the JDBC ODBC server interface where you can run those JDBC ODBC connections and run those queries. Let's move on and look at Impala. So I spoke about Impala mainly because, and I want to speak about Impala just after Hive, because Impala is pretty interactive. So the query is much more interactive compared to Hive. It's newer. Impala is an MPP SQL engine. So you can do massive parallel processing. So for people who have used like Teradata, Netezza, yeah, this is pretty useful. You can process large amounts of data. It provides low latency and high performance compared to, yeah, Hive. Let's move on. Next one is Pig. So I have not used Pig in any of the projects I've used. I've worked on, but Pig is something. It's an answer to making MapReduce easier, but in a different way. Instead of using SQL for it, people at Yahoo, they developed a processing language which is kind of like SQL, but it's not really. It's a different kind of script. They call it a pig script, and so the goal is still the same. So they don't want every time somebody writing a MapReduce program in Java, which is a bit complicated compared to a SQL or a pig script. So to make life easier, you write a pig script, and then like there's a compiler that sits there that converts the pig script into a like MapReduce program, and then it runs it in the backend. So for you, you don't have to worry about writing those complicated jobs. You write a pig script, but yeah, at the backend, it still runs a MapReduce job. So some people call it pig Latin. and some the pig runtime is what actually runs the job, and in the back end, it's a MapReduce job that gets executed. What are the main features of pig? Extensibility. It allows users to create the custom functioning, so you can write your own functions and you could reuse those functions. So if you write a function to like convert dates from format A to format B, you could store it and then that can get reused again. You could optimize. You can optimize your query so that you can focus on semantics rather than how do you efficiently do this program, right? You don't have to think about efficiency. So that can be done by pig itself. It handles all kinds of data, so you can do structured data as well as unstructured data. The load command in pig loads the data. So similar to Hive, there is a like in Hive, you do a create statement along with the load, or you can do a load statement after you do the create statement. So you can load a file into a table. So if you say it's a comma separated file and it has like 5 columns, and if you load it into a 5-column table, it will take the first column, put it in the first column that you have in the create table statement. So you'll have that structure to it. Similarly in pig as well, you can structure it and then load it into a like structured file using a load command. At the back end, the compiler converts the pig Latin into multiple MapReduce jobs. So you can do a lot of things like joining, sorting, grouping, filtering. It's a bit like you have a bit more functionality than a Hive. So you have much more functionality. So you can have the output stored back in the HDFS file. You can dump it back on the screen. You can do whatever you want. Okay, HBase. So HBase is a NoSQL database. So like NoSQL databases are like highly scalable, like databases that don't have a very strict schema. That is, you don't have to alter the table whenever you add a field, change a field type. You don't have to do that. And NoSQL databases are where you can probably have it highly available. That is, you can have it like have multiple copies of the data without really like worrying about how to have multiple copies of the data. So there are multiple types of NoSQL database, but let's look at HBase for now. So HBase was built on top of HDFS. So HDFS is whenever you have a HDFS data set, or if you have a HBase table, when you do an insert statement, it actually writes the data into a HDFS file. So you can actually go to the HDFS file and look at the data as well. Obviously, if it's not in binary format or Avro or something like that, if it's in normal format, you can actually open it and cat command, or you can do a head command, tail command. You can look at it. It supports all kind of data, so it not only structured, it can also do unstructured or semi-structured. It provides the capability of Google's big table. So that's how the work was based on, and it can work on big data sets. It's a non-relational database, so you cannot join between multiple tables. It's a distributed database, so you can store it in multiple distributed computing systems. It provides real-time read-write access to large data sets. So in Hadoop, you'll have to submit a job to write more data and to write a select statement, or like if you want to read one particular record, you'll have to submit a MapReduce job, or you have to go to Hive that in turn submits a MapReduce job. In HBase, you can just write a query and access that. It's a column oriented database. So what that means is we have multiple columns and column families, and we store each column as a key value pair. HBase has a shallow latency storage, and enterprises use it for real-time analysis. HBase is designed to contain many tables, so you can have multiple tables and each table has to have a primary key. So you can have multiple tables, you can have a primary key. You cannot join between the tables though. So that has to be done in a program, like in whatever program you use HBase out of. So if you read HBase into a Python program, into a Java program, then you'll have to write that logic to actually join these tables or join this data in a different place if you need to join the data. So essentially, we typically, when we design the tables, we don't design it to be um, like um, having multiple joins. So you typically denormalize it, so that all the data is stored everywhere. You're able to read it based on an ID. So what are the components? There are two components: HBase master and the region server. The master, what it does is it maintains and monitors the Hadoop cluster. It performs administration of the database. So whenever you need to administer the database, HBase master takes care of it, controls the failover. DDL operation gets handled by the HBase master. What the region server does is it handles the read, write, update, delete requests from the client. So any requests that come in that go to the region server. It runs every node in Hadoop cluster. That's a Hadoop HDFS data node. So any data node does get controlled by the region server whenever you have HBase installation. So note that there's a like running a HBase installation would actually have all the control of the HDFS by the HBase server. While if you run Hadoop, if you run Hive, it just reads the underlying data that is in HDFS as a table. Like you can read it as a table. So there's a difference. This HBase is actually a database which uses HDFS as underlying data. So we look at an example here. So if the rows here are identified by the email address there. So the one in the left that is pink, that those are the IDs, and we have two column families. One is the user data column family and the pictures column family. In the user data column family, you actually have like first name and last name. Some of them, if you notice that one of that is empty, and yeah, that is acceptable. You don't have to have all columns populated. That's one major advantage of HBase. And the other column family, pictures column family, has the pictures itself. So it has the actual picture that's stored. So column families store the accessed data together. So it stores all the last name together, but it has a key value pair in it. So if you want to get all the people who have the last name as stack, because we have all the last names stored in the same place, we can get all the last names that are there, and then we can look up what IDs or what email addresses they have. Okay, so let's move on to the next one. That's Scoop. Scoop is the one where you can export data from any RDBMS into Hadoop, or you can import data from Hadoop. I think it's the other way around. So when you import the data, you move from RDBMS to Hadoop, and when you export data, you move data from Hadoop to RDBMS. So Scoop imports from external sources. So you can do an import from like Oracle, Postgres, MySQL, and many other. Like you can do from almost any RDBMS, and you can move them into like Hive tables directly. You can move them into HDFS. You can directly move them into HBase. You can do all that using Scoop. It transfers data from Hadoop to other external sources as well. So it can also work with Teradata, MySQL as well, Oracle. Scoop can process structured data. It can also process unstructured data. I mean, it can process a JSON. I don't think it can do a blob, which actually stores say image files or video files, binary large objects with all the information about a JPEG. You can move that over. So it can process all that. When a Scoop command is submitted, it does multiple subtasks in the backend. These are all map tasks. So there is no reduce. When you do a scoop, each record is processed one at a time. So like after the SQL is run in the RDBMS, say if the output is like 10 records, all the 10 records need to be processed the same way and written to HDFS or Hive. So there is no reduce that is needed. All those are mapper tasks. So all the tasks that happen during a Apache scoop, whether it's import or export, are going to be mapper tasks. So scoop export is very similar. It just works the other way around. It exports the data from Hadoop into the destination database. Next one we're going to look at is Spark. This is again one of the most important libraries you will have to learn as a data engineer. It unifies all kind of big data processing. Spark has built-in libraries. It can do Spark streaming, Spark SQL, Spark machine learning, Spark graph processing. So it's called GraphX. So all that can be done in Spark. So it kind of does a lot of work that multiple libraries that Hadoop ecosystem was doing separately. More than that, Apache Spark is more really really being adopted heavily, especially using the Databricks platform, because it is really fast. It can do batch processing, stream processing pretty efficiently. So it can do like you can write stuff into a like a Kafka um, or a messaging queue, Rabbit messaging queue or something like that. All that can be stream processed in Spark pretty fast, or it can also do batch jobs just like Hadoop does and process lots of information and do it much faster than Hadoop does. MapReduce job does. This is done using a DAG scheduler. So we looked at the DAG scheduler a little bit earlier. So similarly here in Apache, when we write a job, it gets converted into a DAG scheduler based on multiple tasks and the order in which it happens, and then it gets executed. There's also a query optimizer, and there's a physical execution engine. We'll look about we'll understand more about Spark in a separate session, but to keep it like at a high level, Spark can be run on a standalone cluster mode on Hadoop, Mesos, or Kubernetes. So here what I think is missing is Yarn as well. So it can be run as a like standalone cluster on Hadoop. It can be run on Yarn, Mesos, Kubernetes. So those you can use all those as the job processing engines. And Spark can be run on all those. Spark applications can be run can use like SQL, R, Python, Scala, Java, whichever you prefer. You can actually use it, and it's in the most common ones that you see are PySpark, which is Python, and Scala. Those are the pretty common ones. And SQL is used like if you're not really programming something and you want to like write query to actually connect to the database, like because you're a business analyst, you just want to, or you're a machine learning engineer, you just want to quickly run a few queries. People use SQL as well. So SQL, I think all three are pretty popular. So um, PySpark, SQL, Scala, and Scala is probably also considered fast. Like in one of the programs, I started using PySpark, and then we got a study which said that Scala code can be much faster than PySpark, so we switched over to Scala. Spark offers like 80 high-level operators, so which you can build parallel applications like much faster because there's so many operators. You can use all those. We spoke about this. It has like a separate library for machine learning, Spark MLlib. It has a GraphX for graph processing. It has a like streaming library separately. You can do SQL there. You can do data frames. Just like if you're aware of Panda data frames, it's pretty similar to that. So you can have a easy learning curve to get there. Again, biggest difference between Spark and Hadoop is it performs in-memory processing, like which is much faster than the MapReduce, where it relies on a lot of disk um, write read operations. So the disk IO is really expensive, and because Spark does everything in memory, it avoids all that, and it's able to do it much faster. Okay, that's all I have for today. Thank you so much for watching. If you have any questions, please let me know in the comment below. Thank you so much. Bye.